Almost every graph traversal algorithm is really just an alternating series of looking and visiting. So looking is just when a node looks at all of its neighbors and adds them onto a list, whereas visiting is when you visit the next node on that list. So let's demonstrate this by starting with DFS, which uses a stack or a last in first out structure. I've decided to use a very simple example like the one you're seeing so that there's no confusion about what's happening. So first we look at all the neighbors from 0, which is 1, 2, 3 and 4, and add them onto the stack. Now we visit the last item on the stack, which is 4, then pop it off the stack. Then we switch back to looking, and from 4 our only neighbor is 1. Then we visit 1 and pop it off the stack, and from 1 we look again and add 2 to the stack. Then we visit 2 and pop 2 from the stack, and from 2 we add 3 to the stack. Now we visit 3, but from here something interesting happens. When we look at 4, we can see 4 has already been visited since it's in red and I've underlined it. Therefore we don't add it to the stack. The last item on the stack is now 3, but once again 3 has already been visited, so we skip this one. The next item on the stack is 2, but we've already visited 2. And then the next after that is 1, we've already visited 1. And then the algorithm stops. And BFS uses a queue instead of a stack, which is a first in, first out order. So once again we look at all the nodes from 0 and add it to the queue. And since this is a queue, we visit 1 instead of 4. And from 1 we look at 4 and add it on. Now from here we don't move on to 4. Because it's a queue, remember, we move on to 2. Now we look at 1, but we've already visited 1. So we skip this step and we visit 3 instead. And then we look at 2. But we've already visited 2. So we skip it again. And lastly we visit 4. And we look at 3, but we've already visited 3. So the next free item in the queue is 4, but we've already visited 4. So I hope it's obvious what's happening now. Both BFS and DFS are virtually the same algorithms. The only difference is the order of traversal is just determined by whether we're using a stack or a queue. So every time you visit a node, we'll simply add on that node onto the visited set, and our stack is simply just an array. And the entire algorithm runs on a loop until our stack is empty, meaning we visited every node. So remember, when we're visiting, we're grabbing the next node on the stack, and then we're checking, has that node been visited? If it has, then we skip it and move on to the next node. If it hasn't been visited, then we want to add it onto our visited set. If the node is the goal state, then we want to stop here. So remember, looking just means a node looks around to all of its immediate neighbors and adds it onto the stack. So I've already implemented this, which is get neighbors. You'll have some sort of get neighbors function, which will grab all of the neighbors of a node. It grabs the neighbor and the weight, but remember, in DFS and BFS there is no weight. Now when we have this neighbor, we want to double check, has this neighbor been visited? If it has, then we don't want to add it to the stack. So we move on to the next neighbor. If we pass this if statement, meaning the neighbor has not been visited, then we want to add it to the stack. And then we just keep doing this on a loop until we've added every neighbor onto the stack. And then from there we can go back to visiting and visiting each neighbor. So this is the fun part. This is how I'm going to take you from DFS to BFS. And it's as simple as this. We're just going to rename this to BFS, rename this to Q, however, in a queue you're popping off the first item on the list, which is our index 0. And just like that, you've done BFS. So in UCS or Dijkstra's algorithm, we introduce a new variable, which is the weight of the edges, or the cost to move from one node to another node. And secondly, we're using a priority queue, or a min heap, as our list. And in this example, for simplicity, I'm just going to represent it as a sorted array. You might have also noticed there's a second number inside each node, and this is to track what is the current best cost to reach that node. At the start of the algorithm, we just say it's infinite or a very large number. So just like before, we look at the neighbors from 0, but this time we add the cost to reach each node to the heap. And since 3 is less than 5, we have 3 at the front of the heap. And an additional extra step we take is to update the best cost values for each node to 5 and 3 in node 1 and 2. So when it comes to visiting, since 3 is less than 5, we visit 3 and pop it from the heap. And from node 2, we look again. We see that the cost to reach node 1 is 3 plus 1 or 4, and 4 is less than the current best, which is 5. So we update it and we cross it out from the heap. Also, let's say it wasn't less than 5, then we simply just do nothing and don't add it to the stack. We also see the cost to reach node 3 is 3 plus 9, which is 12, and this is the largest number in the heap, so we've pushed it all the way to the back. Now when we look at our heap, 4 is the next best value, so we jump to node 1. And from node 1, when we look at node 3, our cost is 4 plus 5, or 9, which is less than 12. And finally we visit 9, which happens to be our goal state, meaning we can stop the algorithm here. Okay, so first of all we need to add a heap, and we introduce a new variable which I've already implemented into the node class. Now you would think, just like in BFS and DFS, you would just add our start node into the heap like this, but we also have to add the cost separately. And the reason why is because a heap needs a value to determine how to order itself. And so we have to pass a tuple where the cost is the first value and the object is the second value. And so this will sort of automatically sort our list. This can be a bit confusing if you've never seen a heap or a priority queue before, although I could make an entirely separate video on that if you'd like. So for visiting, just like in BFS and DFS, we have to pop off the next item in the list. In this case we're popping off the value with the lowest cost, and we're doing the same thing as before. The only difference is, if a neighbor has never been visited before, we only want to add it onto the heap based on a condition. And that condition is if the cost we found is better than the current best, which you should remember from the demonstration. So once we have our neighbor, we want to calculate what the new cost is to reach this neighbor. So it will simply be the cost of the current node plus the weight to that neighbor. And then if this new cost is less than the current best, and only in this case do we update the cost of that neighbor and then add it onto the heap. So I'm not going to bother demonstrating A star, and the reason is because it's practically the exact same as UCS, and the only difference is this thing called a heuristic. So first of all we have a terminology change. Cost now becomes G cost, but it's exactly the same thing. Now we have this new thing called H cost, which is our heuristic. And a heuristic is just a guess or an estimate that sort of guides the algorithm in the right direction. In this case, the heuristic is the distance from the current node to the goal node, and we'll go more into that later. And all we do in A star is we add these two things together, and we call that F cost. And I like to think of that as the full cost or the final cost. And really, all this comes down to is just this singular line of code here. Instead of pushing on the normal cost onto the heap, we calculate the F cost and add the F cost onto the heap, but virtually everything else is exactly the same. So the heuristic looks something like this, where you take the node and the goal node as input, and we just perform a simple distance calculation. If you have like a 2D game where you can only move up, down and left and right, then Manhattan distance is suitable. Whereas if there's no restrictions, you can use something like Euclidean distance. There's also stuff about admissibility, I'm not going to go too deep into it just to not make this video confusing, but all it's saying is you should never overestimate the heuristic, or else sometimes it won't find the optimal path. And there we go, just like that we have the A-star algorithm. And we defined our h-cost, which is the heuristic from the start, and note how our f-cost will also be equal to the heuristic, because it's a 0 plus the heuristic. And then here we're just adding on the f-cost rather than the normal cost. And then from here we're popping out the f-cost rather than the normal cost. Here everything stays the same. And in UCS this line is exactly the same, but we just renamed it to g-cost. The only difference is here we're also getting a heuristic from the neighbor to the goal. And then instead of comparing the normal cost to the neighbor's normal cost, we're comparing the f-cost to the neighbor's f-cost. And if our new f-cost we've calculated here is better than the neighbor's current best, then we're allowed to update it. So we update the g-cost, and we update the h-cost, and we update the f-cost all individually. And then we're adding on the f-cost onto the heap instead of the normal cost. And that's it. That is the A-star algorithm. And I hope I've made it clear now that these are all practically the same algorithm. The only difference is the order of traversal. So in DFS we're using a stack, in BFS we're using a queue, in UCS we're using a heap, and in A-star we're also using a heap, but we're just ordering it by the f-cost. So now that we've done all 4 algorithms, I think it's good to demonstrate how all of these work. So let's say we have this node here, and we have this node over here. And you could see instantly how A-star found the best path almost immediately. So I hope you enjoyed that, and I hope it was fun. Any other video, that algorithm or data structure that you want me to explain, we can do that. And thank you for watching, and see you next time.